If the energy that is liberated in photons is eta mc squared, we can define that the mass accretion rate, we can divide both sides by the time, and then you can define that the mass accretion rate as mass over time. And the left-hand side here is the luminosity. So I have an expression for the luminosity of accreting matter around the black hole. If we know the AGN luminosity, then we can deduce what its mass accretion rate m dot is. Now in units of 10 to the 42 ergs, this gives you about 0.02 solar masses per year. That means that an active galaxy consuming about 2% of a solar mass per year would shine with a luminosity of 10 to the 42 ergs per second. Compare that to the luminosity of the Milky Way central region, which is only about 10 to the 36 erg per second. That implies either a very low infall rate at the present moment, meaning m dot about 10 to the minus 9 solar masses per year for the Milky Way, or a low efficiency, or both. That is because the Milky Way has no gas in its central region, so it is not an active galaxy. You might think that by shoveling in matter at higher and higher rates, you can make an AGN have arbitrarily high luminosity. Well, in fact, there exists a maximum permissible luminosity for a given black hole mass. If you crank up the luminosity too high, the gas surrounding the black hole will be blown away by the radiation pressure. Now consider an accreting black hole of mass mbh and luminosity eta m dot c squared. Let's assume that the black hole is surrounded by ionized hydrogen. At the distance r from the active nucleus, the photons have an energy flux equal to the luminosity over the area. Now, in addition to an energy E, each photon has a momentum P equal to E over C. You remember that the pressure is the flux over the speed of light. Don't confuse here the little p, which is the momentum, with the capital P, which is the pressure. This is equal to the luminosity over 4 pi c r squared. Now, because the photons carry momentum, they can exert a force on the free electrons and protons in the ionized hydrogen. The force exerted on each particle is the rate at which momentum is transferred to it. The rate of momentum transfer depends in turn on the particle's cross-section for interaction with photons. Electrons have a much larger cross-section for photon interactions than protons do. For electrons, the relevant cross-section is the Thomson cross-section, which is about 6 times 10 to the minus 25 centimeters per centimeter squared. The electron experiences an outward force due to radiation pressure. The amplitude of the force is equal to the pressure times the electron cross-section. Remember, force is equal to pressure times area. Now the area here is going to be the cross-section, the electron cross-section, and the cross-section of the electron times the luminosity over 4 pi c r squared. Now this force, this outward push, is being counterbalanced by the inward pull of gravity. Now the inward pull of gravity is on the electrons and the protons. As electrons accelerate, it drags the nearest protons along with it, which maintains the charge and neutrality. Thus, every electron is burned by a massive proton that is dragging along. So the inward force would be the force of gravity. It's minus g times the mass of the supermassive black hole times the mass of the proton over r squared. Now, if you equate these two forces, then you have the Eddington limit. It's a situation where a gas parcel is in equilibrium between the inward pull of gravity and the outward push of pressure. Now you can solve this for the luminosity, call it Eddington, and that gives you the Eddington luminosity, which is the luminosity at which the outward radiation force exactly equals the inward gravitational force. And that's the maximum luminosity possible for an accreting black hole. Now notice that the factors r squared cancel out, which shows that the ratio of the radiation force to gravitational force is independent of the distance from the black hole. So solving this for the Eddington luminosity, you have 4 pi g m. M here's the mass of the proton, C sigma e times mass of the black hole. And substituting the values, this gives you about 3 times 10 to the 12 solar luminosities for a black hole of about 10 to the 8 solar masses. Now, if the luminosity is greater than the Eddington luminosity, that means the pressure is winning and the ionized gas will be accelerated outward and accretion will cease. So the existence of a maximum luminosity leads to a maximum mass accretion rate for black holes, which is a luminosity over eta c squared, which gives you about 2 solar mass per year for a black hole of mass 10 to the 8 and efficiency 0.1. If you try to feed a black hole more rapidly than this, it spews the gas back out. Notice that this maximum mass accretion rate naturally provides a unit to measure mass accretion rates. You can measure, for instance, the mass accretion rate as the absolute mass accretion rate over the Eddington mass. And we refer this as the Eddington ratio.